From ContainerDays Hamburg, this video is proudly presented by Dux IT.
My name is Sohan. I've been in the industry for 16 plus years, which in the tech world I hear is at least like 40 or 50 years. So I've really seen a lot of changes over the past few years. I work in a startup called AuthZ. We're in the authorization space. Fun fact, it was started by the three people who wrote Quay, who in the previous talk, there was a demo of Quay. So there's a long lineage of cloud-native experience and containers. And I'm here to talk to you specifically about low-latency workloads on Kubernetes. And these are some of the lessons that we learned from SpiceDB. Two things I want to specify there. One is no two workloads are the same. So what might work for us and for our workloads may not work for you or may work really well for you. And two is we've been doing this 5 years now. So really the credit is to our amazing engineering and product teams. I'm hoping I synthesize all of that knowledge and present it to you today in a way that is useful for you. Low latency, just to context set, can mean many different things. And even if you're specifically, say, a backend developer, this could mean different things. It could mean a different thing for a game dev versus an embedded system dev. So just to context set, I'm specifically talking about network services with single-digit millisecond SLAs, service level agreements. We're not really talking about things like soft and hard time. We're not talking about latency in the form of, say, a pacemaker, where someone's life is literally in your hand. Or we're not even talking about, like, say, an air traffic control, where, again, low latency can mean something different. What we are talking about is, say, if you're building a website to allow for trading, where even a millisecond can make a difference, and that is over the network, so that's what we're referring to. And typically, for today, I will talk about a garbage-collected language, and of course, running in the cloud. So for those of you all not familiar, we are going to be talking about our experience using SpiceDB. So what is SpiceDB? Essentially, it's an open source graph database optimized only for authorization queries. The name might suggest it's a database, but it's not a general purpose database. Essentially, it is only optimized for authorization. So you can look at the diagram there. So it's a centralized version of authorization. You can have your apps, your microservices, your data warehouses, and all of them will reach out to SpiceDB to check if something has permissions. And you would do that via an API, which could either be in gRPC or HTTP. SpiceDB is written in Go. And the sort of questions you can ask SpiceDB are, can a subject take an action on a resource? For example, can me, Sohan, edit document 1? You can also say something like list all the subjects or list all the people, for instance, that can edit document 1. Or the reverse, list all of the documents that can be edited by a certain person. So if you want permissions in your app, that could be a document app, a repository app, or even a financial services app, you can use SpiceDB. And interestingly enough, SpiceDB is actually based on a Google white paper. So I'm going to give you a bit of history now. So in 2019, Google released this white paper called Zanzibar. And this is named after Google's internal authorization system, also confusingly titled Zanzibar. Now, there is a long lineage of internal Google services being used in the open source world. And the most famous example is, you would know, it's also the topic of this entire conference, it's Kubernetes, of course. Right? We know Borg was the precursor to Kubernetes, started as a Google service, and now all of us use it. So in 2019, this white paper was released, and it made waves in the identity and access management space, because most of y'all will probably use something called role-based access control, RBAC, where you're tied to a role, and all roles can do a certain thing. Or you might use something called attribute-based access control, which, everything has a bunch of attributes. When you want to make a decision, you check all the attributes, and then a decision is made. But those two systems don't necessarily scale very well. So for Google Scale, they needed something different. So they introduced this concept called reback, or relationship-based access control, where there are relationships between users and objects. So at any point of time, if you've used any Google service with logging in, you've probably gone through this Zanzibar method internally, where there is a relationship between, say, your ID and a document or a YouTube video or a map. And SpiceDB is based on this. Knowing all of this, you will know that permission checks run before any other work is actually done. If you log into your Google Drive, there has to be a permission check with all of those documents before it loads. And if you immediately hit the refresh button, that permission check has to run again, because maybe someone's removed you from a document, so you shouldn't be able to see it. So this means authorization is on the critical path, which means low latency is extremely, extremely important. And at the same time, you need scale. In that Google Zanzibar white paper, they mention they had a scale of 10 million client queries per second, and this was back in 2019. At the same time, we have also done load tests. You can read the blog post, where we could do 1 million requests per second against 100 billion relationships. And we used OddZ Dedicated, which is our product, on AWS EKS with CockroachDB as our data store. And the latency we observed was 5.76 P95 latency at 1 million reads per second. So we need low latency at scale. So how did we actually design for low latency? And here's the core of today's talk. The first thing you need to know, most important, is there is very often a confusion about whether you're designing for low latency or high throughput. And those are completely different things. Throughput is basically about how many requests per second you can handle. And if you confuse that with low latency, you're actually going to introduce more tail latency in your system. If you're building for high throughput, you have to think of buffers, queues, batching, and so on. And all of this actually adds more latency to your system. With low latency, it is slightly different because it is instead prioritizing predictable response times. The metric people use is things like P99 or P95, which basically indicates the response time below, say, 95% of requests which are completed. Right? So make sure you know which one you're actually designing for. And when it comes to designing for low latency, again, there are two different things. There's how do I write a low latency system, and then how do I run a low latency system? For the purpose of today's talk, I'm largely going to stick to the things that are cloud native specific. There are lots I can talk about in terms of Go code and data structures and garbage collection and so on. I'll maybe touch about it a little, but largely it's to do with the cloud native ecosystem. So a little bit about writing low latency. I'm semi-joking when I say this, but it's also true. You have to keep your system as simple as possible. And of course, right now in the audience, you're going, well, of course, this is obvious. But performance really is a battle against complexity in your implementation. Because here's the thing. Every time you build a system, the idea is to profile as much as you can. You have a hypothesis saying, this is how my system's going to work, and then you profile it with some of the tools that I showed you there to really see what's going on under the hood. And while profiling, your computer tells you two very convenient lies. One, it tells you about concurrency control, right? The language or the operating system you're working on, it tries to convince you that a single core can actually do more than one thing at a time. But what's actually happening under the hood is that a process starts, and then it switches to another process, and that process starts again. Right? So it's trying to tell you that it's actually working on two different things, but not really. So you need to actually have a bunch of abstractions for these higher-level concurrency patterns. And this includes things like control over your concurrency limits and prioritization of tasks. At the same time, when profiling, you can look at memory control. Again, a convenient lie your system's telling you is your process or your programs have unlimited memory because you're running these things and your system is doing like garbage collection and freeing up memory in the background, but we know that's actually not true. The sort of hot take of today is that garbage collection is kind of okay. I think it's okay, as long as you have some means or some way to control this allocation. So really look at how you can tune garbage collection for your workload. And honestly, the best thing you can do for this concurrency limit is to try and parallelize as much as possible. Right? The design of SpiceDB is kind of inspired by CPU design, in the sense that CPUs aren't necessarily getting as fast, or they're not scaling as much as they used to, but they're getting more dense, right? So, more cores and so on. So really, it's about trying to parallelize computation with how you write your code. And you can see in the diagram, we have multiple pods there. So each of them actually run SpiceDB. Excuse me, and they are all self-discovering. So they self-discover other pods on a cluster, and they shard up the work in between these different pods. And it's not just random sharding that happens, because the two requests might actually share the same underlying computation pattern when sharding up, which actually saves on some latency and enables us to get low latency. So try and parallelize everything. Now, this is easier maybe for our use case again, because what's actually happening under the hood when a permission check comes in to SpiceDB or any Zanzibar-like system. So I'm going to give you the example of a thing like Google Docs. Right? You have all these relationships, and they are represented in the form of a graph like this. So on the left-hand side, you can see some document. And on the right, you can see all of the users who have relationships with this document. Some are readers, some are writers, and some belong to an organization. The key thing here is see the dotted line between reader and writer. This implies if someone's a writer, they can also read a document. Again, this is what's happening behind the scenes when you log into Google. So say a permission check comes in to see if Jill is a reader of some document. What happens is the check first goes to some document and then reader, and you see the names Fred and Kim. It's like, nope, Jill's name's not here. And then it goes to writer and says, OK, Jill's name is here, and there is a unidirectional way to get from some document to Jill via reader. And that is how permission is given. Similarly, if the permission check was, can Fred edit this document? There is no unidirectional way to get from some document to writer to Fred, and hence Fred can't edit this document. The thing is, when I spoke about sharding up work, we have computed all of these things when we were making the check to see if Jill is a reader. So say another request comes in to say, is Fred a reader? We have already made that computation. So this way, we can shard up work between different pods and really divide and conquer to get that low latency. Speaking of making calls, there's something called a single flight request. And I'm quoting directly from the Zanzibar white paper, which says, we found the handling of hotspots to be the most critical frontier in our pursuit of low latency and high availability. What is a hotspot? Well, imagine a YouTube video has gone viral and lots of people are trying to view it. Or a document has been shared with an entire organization, so everyone is clicking on it. So it needs to be available to everyone at low latency. What single flight request basically does is, if a system is serving a request and a new request comes in for the same thing, we essentially just return the result of the first one back to both. And this allows for a task system that's controlled by priority and also a function called deduplication. So the same call is not made hundreds of times. It's actually just a single flight, and again, that leads to low latency. And speaking of requests, we also use request hedging. Now, for those of you all not familiar, the idea basically is, say you make a call to a backend service, you can define a window and say, if I don't get a response within this window, I can make a second call to that same service. So basically, you're hedging your bet between two of these and saying one of them will return to me in a window that I'm defining. Now, this can be tricky. It could be a double-edged sword because you don't want to be making too many requests, right? Like immediately, something doesn't return a response, you don't want to send another one. So defining that window is some experimentation involved, but you can actually really save on your latency here. Again, giving you an example from a white paper by Google, the Bigtable team discovered that firing a second copy of a read after 10 milliseconds cut their P99.9 latency by 96%, which is a huge number. And it didn't involve increasing their CPU and memory because it was just 2% extra traffic. Of course, if you want to do this for, say, P95 latency, you will probably increase that number a little more. It comes down to math, essentially, because if you know your P99 latency, which means 1% of your requests are not served in a certain window, so you can take a bet and be like, OK, if I request hedge, there's a good chance it's going to come back in my P99 latency. So look at how you can do request hedging while writing for low latency. So we spoke a little bit about the writing for low latency part. Let's go on to the running for low latency. The interesting thing for me is things like authorization now are moving into platform teams, into DevOps teams, because it's been centralized, as opposed to maybe 10 years ago, where developers wrote their own custom authorization. So this part is also relevant for everyone here. And a small plug, basically, for how we run low latency systems is all of OddZ's products run on Kubernetes, and we have had as much cloud native experience as could be possible, since a lot of them have been there since the early days of Kubernetes. And these are some tips and some things we've learned along the way. The first one is Kubernetes defaults. Now, by default, Kubernetes is best effort, and you probably already know that, but it actively must be bent to serve low latency workloads. The sort of analogy here is that little password on your Linksys router, which is admin or ABCD12345. For most of us, it's fine, but for some people, they're like, hey, no, I need to change that password right now. So when we wanted to run low latency workloads, there are a few things we needed to change to make sure that Kubernetes was not doing just the fairness thing or just the scale thing, but also doing it for low latency. Because sometimes a pod could share a noisy neighbor, right? Sometimes you could get a memory overcommit. Also, Kubernetes could maybe do a random co-location where you're co-located with the noisy neighbor, or you're co-located with the replica, that node goes down, and you're in trouble. One of the ways to do that is by this primitive called a taint and a toleration. The general idea is an affinity or the anti-affinity, where essentially you're telling that these pods are attracted to these nodes. And anti-affinity is the opposite. And with the primitive of a taint, you're essentially telling a node to repel a set of pods, saying, do not run this particular pod. And tolerations can be applied to pods, and they work with taints. So you're telling the scheduler to schedule with matching taints. You can see in the primitive right at the bottom, I mentioned tolerations with like a key and an effect. Essentially, what this does is you can have hardware specified to run certain pods. So using a combination of taints and tolerances, you can say, have these pods run only on this specified hardware or this node pool, which is specific to our workload. A question that we've got asked here is, hey, maybe you can also use a node selector, which is more specific. But again, the idea about low latency is, you're sort of limiting the upper bound. It's not about best case, but you're limiting the upper bound. And for that, taints and tolerations probably jive a little better. The next thing we learned is requests and limits. Now, if you Google, like, how do I build low latency workloads on Kubernetes, this is probably the answer you'll get, and for good reason. Because with a request, you have minimum guaranteed CPU memory or resources. And with limit, it is the upper level, right? So the maximum available limit to the pod that is reserved upfront. And what this means is it makes your workload extremely predictable, which is very good. But there are some cons as well. Some of the pros include no more killed, so you won't get randomly killed by anything. You might get killed by Kubernetes, though. But Kubernetes knows which processes is actually taking up more memory, and it picks the right process to actually kill you. But there are some cons to this approach. One is limits actually artificially limit processing. Sometimes, maybe your node can actually process a lot more, but you've set certain limits, so it's making it very artificially limitable. And they're also very reactive, because Kubernetes is polling to check if something is acting outside of the boundaries that it's supposed to be. So it is very reactive, so only if something happens, it can do that. And lastly, pods will still suffer from context switching. Let me explain, and I'm going to jump into an aside here. There are, again, going back to that concurrency limit that I told you about, right? There are two things that could potentially happen. On the top, you have parallelism, where you have process A running, you have process B running at the same time. Concurrency is when you have process A running, and then there is a switch to process B, and then there's another switch back to process A. And that switch can happen in a couple of cases. The one is a cooperative scheduling where there is an event trigger, like, say, a syscall, saying, hey, switch to process B. Or it could be preemptive scheduling where beforehand the system's decided, at some point of time, I'm going to switch from process A to B. You want a little more of the parallelism and not as much concurrency, right? Because if you think about it, this has overhead as well. Saving and restoring context is overhead, which affects latency. CPU cache getting invalidated is latency. And this is not just happening in your Linux kernel. This is happening, say, in Go. This is happening in your core if you're using hyperthreading. So it's a lot of context switch, which causes overhead. So this is very expensive. One way to sort of solve for this, which is basically one of Kubernetes' last feature, which maybe not as many people use as I think at least they should, is the static CPU manager policy in Kubernetes. Now, this was stable in v1.26, which was a while back. And essentially, it allows you, it's meant to be a solution to this problem of context switching overhead, where it allows containers with integer CPU requests exclusive access to CPUs. The only drawback of this is it is static, right? So you have to sort of do it beforehand, but it reduces any context switch or cache thrashing that happens when the switching is happening. There is one way to solve for this being static, though, and that is by the use of Carpenter. I'm sure a few of you use it already, and many more are familiar with it. Carpenter was launched 3 or 4 years ago by AWS as an open source framework, and now it's been donated to the CNCF, so it's available for everyone to use, and it's not tied to a company. And essentially, Carpenter is a Kubernetes node autoscaler. So it provides just-in-time capacity, and it provides it dynamically, right? In the past, there were things like cluster, autoscaler, et cetera, but Carpenter seems to be popular in the industry right now for things like unschedulable pods that need just-in-time capacity. The cool thing is, of course, it works well with AWS EKS. Azure AKS also used to use cluster autoscaler, but now they have support for the Carpenter primitive. GKE has something called Autopilot, which is still running strong, but about a month or two ago, they announced the launch of Carpenter in preview mode. So right now, there is support for the Carpenter primitive in GCP, but it's in preview mode. And yeah, this basically brings the just-in-time capacity, and it limits the fact that you have to permanently over-provision for this. So you can actually do it dynamically with things like spot instances. So as a summary, basically it's all about isolation, isolation, isolation. In fact, our core product is infrastructure to run SpiceDB, which we call auth dedicated, which is pretty much an air-gapped installation for our customers, which we know exactly, we are very aware of the environments. Environments can be very opaque, and with the more complexity and layers and abstractions you add, you lose out on visibility into each of those layers. So try and build that awareness of the environment. And in fact, it's so important for us that isolation models are built into our documentation, into our product marketing, and into all the design patterns when we speak to customers as well. All right, so for next steps, if you're interested in learning more about this sort of stuff, honestly, the Zanzibar paper is great. It's 14 pages. It's not written in academic language. It's very readable. There's an annotated version on zanzibar.tech. So on your train ride home, just quickly read it. It's interesting if you like things like distributed systems. And SpiceDB is open source, so feel free to jump in, contribute, learn from it. There's also a SpiceDB Kubernetes operator, if you want to check that out. And the blog that I mentioned about the performance testing, if that's the sort of thing you enjoy, is on the post there. I hope you learned something new today and enjoy the rest of the conference. Connect with me on LinkedIn, and thank you.
What about the throttling issues that comes with CPU limits? CF Nathan Yilling blog article. Have you tried removing CPU limits for latency-sensitive workloads?
Yeah. To be honest, I haven't read the article, so I might need more context. But yeah, low latency in general is a tricky thing. For instance, we deploy on different clouds, the hyperscalers, which themselves have a bunch of latency SLAs and stuff. So those things are actually just pretty much written into contracts, right? There are some things we can control. There are some we can't. So yeah, that happens. That being said, we have definitely seen performance of latency when we run on differentiated hardware, right? So running on a certain kind of hardware, like say an ARM versus Intel versus whatever, we have seen improvements in latency, and issues like throttling go away. So again, I'd say look at your workload and see where it performs better, and yeah, and there. But I will check out Nathan Yellen's blog for more context.
TLDR, the article says, in the end, you should remove CPU limits.
Okay.
As shrinked as possible.
Yeah.
That's the idea behind it.
Yeah.
When you talk about low latency, specifically single digit, you cannot ditch NUMA layouts. Mm-hmm. Did you perform any CPU pinning to match NUMA layouts with Kubernetes?
Sorry, can you give me a context about what NUMA layouts is? Who was asking?
To pin some CPUs to several workloads.
Oh, okay. Yeah. CPU pinning. Yeah, I mean, I did mention the whole affinity and anti-affinity. So some workloads and some pods we specifically want to run on hardware optimized for those workloads. So yeah, we definitely do that. I think, again, the TLDR is we found that taints and tolerations work better for low latency than straight-up node selections, where you're pinning it to a CPU. And again, it really depends on what your use case is. With low latency, you want to, again, have something that is for the average as opposed for best case. So we found that taints and tolerations work better in those cases. So.
Another question, you said less OM kill by limits, but isn't actually reaching memory limits causing out of memory for a pod versus reaching CPU limits only throttles CPU?
Sorry, I'm just trying to pass the question. You said like...
It's about the fact that so when you put a memory limit and you consume all the memory allocated, automatically you go into out of memory issues.
Yeah.
Rather than when you place a CPU limits, you are not killing the pod or the application doesn't really dies. It only throttles, which in the end might be even worse in some cases.
Yeah, yeah, definitely. The CPU does throttle, and it can cause problems where, like, the node is not reachable. So I think that's what they were referring to. I'm not sure. I know. Is the person here?
Who asked the question?
Yeah. Okay.
Yeah, I just wondered, you said, or you showed in one of your slides where you explained the limits, or that you should use limits, that you said on the pro side, with this you would reach less OOM kills. But actually this is what I argue against, because as soon as you introduce memory limits, you will reach OOM kills, because it is not best effort anymore, but reaching the limit immediately OOM kills. That's why I'm wondering why you put it to the pro side, so that you do not have OOM limits anymore.
So at least we've noticed that it, how do I put it? Like, are you referring to, let me just confirm what you're, like this one, right?
We're not saying, but
yeah. So yeah, I mean, the thing is, it's more about predictable performance. Yeah. You know, you won't get kill by the kernel, but essentially, yeah, you do get kill by Kubernetes, which sort of picks the right process to kill, so it makes like the performance a little more predictable, right? If you get kill by the kernel, maybe a process that you don't want to dies off, and you know, that again affects our metric on latency. So.
One last question before the after party. Someone in the audience? No, don't do meh. I'm sure you have questions. Questions, anyone? 3, 2, 1. All right, let's go for the after party. Thanks a lot for your talk.
From ContainerDays Hamburg, this video is proudly presented by DAX IT.